Okay, so now let's go and look at the definition of force. Of work. Okay, so of work done. When we say work, it really doesn't make sense. It's always work done, or something does work. And like I said, there's a fine print. It's always on something, on the object of interest, by a force. Okay, a force does work. Okay, so I can do work as well. So it's always do work. That's the adjective for it. Or the verb, I should say. So I can do work, but really I'm creating a pushing force on something, and then it's the pushing force that is doing the work. Okay, so now it's saying the definition is it's the amount of force applied over a displacement. But I like to add, so if you read any book, it will say that, but I like to add is the energy needed for the amount of force applied to the amount of force that's applied over a certain amount of distance. Okay, so let's look at the simplest case is if the force is parallel to the displacement. Okay, and we'll generalize and look at how about if the force is not parallel, so not parallel to dr, and then what if F is not constant? Okay, so here I should say it's a constant F, and then we'll look at not constant, sort of the most general case. Okay, so the simple case is if there's a box, right, and I push 10 newtons and it moves a displacement of, so this is a pushing force, and it moves a displacement, and this is all in the x direct, all in one dimension, right? And it's parallel. So what is the displacement? The displacement, if I move 2 meters, right, it goes from here to here. So my displacement vector is this way, right? So yeah, so that's that, right? So the work done is just the pushing force times dx. Okay, delta x, I should say. Then that's 10 times 2, 20 units is joules, because it's really a form of energy. It's how much energy you need to apply this force over 2 meters. Okay, and that's the end of it. Extremely easy. Now, if I push it in a perpendicular way, right? If I push it this way with 10 newtons, and it moves this way for 2 meters. Okay. So this is my pushing force. This is my displacement. Okay, displacement is final minus initial, right? So let's say 0 is somewhere. So the final position vector, Rf, minus the initial Ri, this minus this is really from here to here, right? So you can, all right, so what would be the work done? So you might think, hey, if I, let's actually have that push it downwards. Let's say I push it downwards with 10 newtons. Okay. So if I push it down and it moves that way, first of all, it doesn't make sense. It must be moving that way for some other reason. Okay, and also, yeah. So if I actually push it down and move that way, also Newton's first law tells us that if it's originally moving, as long as there's no force that is pushing against it, like friction, then it's just going to go on forever. So the fact that it moves this way has nothing to do with my force. So at first you might think I'm still doing work, right? Now that's your using your everyday life understanding of what work is. Here we need a rigorous definition, and you need to understand it's on something by a force. The fact that it moves this displacement has nothing to do with you pushing here. Okay, so the work done what we are going to say, if I say it in English, it will be work done by the force P is equals to 0. It sounds counterintuitive because I'm pushing P downwards, but it's not going downwards. So I haven't done, so P has not done any work. So this is the crucial bit. Whenever you find yourself running into counterintuitive results, whenever you're telling of work done, ask yourself, is the work done by the force? Okay, work done is by the force. I'll highlight that 5 times. So it's moving that way, but it's nothing to do with P. It's moving that way because of some other reason. Maybe there's another guy with force F pushing it this way. All right, so work done by F, let's say F is pushing, F is pushing 20 newtons, whatever, or let's make that 2. Okay. So the work done by F is some number, 2 times 2, so it's 4. So work done, let's actually write that down, right? Work done by the force F is equals 2 times 2, right? 4 joules, right? 2 newtons times 2 meters, 4 joules. But the work done by P is 0. Now it makes more sense, right? Because F is really doing the work in the colloquial sense, and P is not doing any work in the colloquial sense. Now it matches up a little bit more. Okay, you're pushing it down, but it's not going there, so P hasn't really done any work. It's moving there for a different reason. Okay, so okay, good. So you understand why that is 0. And now one more case is, what if it's anti-parallel? So if I push it this way with 10 newtons, and it moves this way for 2 meters. Okay. So what is the work done by P? What we are going to use with our definition, because it's going to be a dot product, it's going to be negative of this times this. So the work done is going to be, because it's against each other, so work done by force P is going to be negative 10 times 2. Okay, so you add a negative, let's actually write this out, negative of the magnitude of that times the magnitude of that. So the negative you shoehorn in because they are anti-parallel, okay? We'll see in dot product, you don't have to shoehorn anything, it's more general, but we will get minus 10 times 2, so we get minus 20 joules. So what does that mean, okay? So one way, it's again counterintuitive, this is why work done is so confusing to a lot of students, is because you try to think of this as the everyday life understanding of work done. And I try to discourage that. Just think of this with a definition. So this is the definition is, if they are parallel, multiply it together. If they're anti-parallel, multiply them together with a minus sign. If they're perpendicular to each other, it's always 0, okay? So that's the definition. We'll write it in dot product, so we don't have to memorize 3 different rules. We just memorize 1 rule and it takes care of all the cases, right? But yeah, so don't try to think of it intuitively. I can try to help explain it, but if it doesn't make sense to you, ultimately don't do it. If it makes sense to you, good. Okay, so here's my try, right? So if you push it this way and it moves that way, not only are you not doing positive work, you are, it's trying to move that way, but you're pushing that way. So you are actually working against it. Okay, that's my best way of this, giving you an intuition. You're working against it, so there's a minus sign we have to shoehorn in. Okay, so finally, that takes us to the general case. If you can consider that for A, B, C, D. Right? So the first case, if it's parallel. The second case, if it's perpendicular. The third case is if it's anti-parallel. The fourth case is a general case, where if I push it this way and it moves this way. So that's displacement, okay? So how much is the push really contributing to it, to the displacement? So that's the best way to ask, to understand work done is, how much does the force contribute to the displacement? Okay, so you resolve this and you realize it's P cosine theta that is helping it, and P sine theta amount does not really contribute to it. So you can think of P as 2 forces, as this force plus this force, right? Because this vector plus this vector gives you P, right? If you move this up here. So you can think of the work done by P sine theta is 0, but the work done by P cosine theta is, so the work done by P cosine theta is P cosine theta times the magnitude of dr. Okay, so the work done by the force P is just P cosine theta times this, because this guy is not doing any work as far as this displacement is concerned. Okay, so it's the amount of force applied over displacement, but it takes into account of the directionality as well. Okay, so now it looks like there is different rules we are using. So it looks like there's 4 different rules we need to remember, right? Sometimes it's just a straightforward multiply. Sometimes it's 0. Sometimes you need to put a minus sign. And if it's at an angle, you need to put a cosine theta. But now as you learn dot product, you realize these all neatly summarized into one single rule is, all right, so now we have done if it's constant and if it's parallel to the force, well, it's just F times delta R, right? The magnitude of these multiplied together. Let's look at if it's not parallel. I can summarize all of them together, and it's the dot product. Okay. And of course, you know the dot product is equivalent to saying this. And you see, yeah, if they are parallel, this basically, now once you understand dot product, you see that if they're parallel, it's just this times this. If it's anti-parallel, it's minus the magnitude of F times the magnitude of the displacement. If it's perpendicular, this is 90 degrees. So this is the included angle between the force and the displacement. If they're 90 degrees, then this is going to be 0. And if it's at an angle, then basically it's the component of P or the force that is contributing to the displacement. Okay, if this is abstract, it is meant to be. And that's kind of one of the reasons I don't like to define energy, which is also abstract, in terms of something more abstract. It's better to define something abstract in terms of something concrete, right? So that's why it's better to define it, in my opinion, with change in kinetic energy. And as you can see with the work energy theorem, it's the same thing. Anyway, so the best intuition I can give you is really this. It's understanding work done is the energy needed to move for a force to move an object for a given distance, okay? Why is perpendicular 0 is because if it moves this way, how much energy do you need to move it this way when you're pushing it this way? Well, it's irrelevant. It's if you push it this way, if you push it this way and you want it to move this way, it's irrelevant. There's no this force is not going to contribute anything to that motion. Okay, so the energy needed for this motion over here, it's 0. I don't have the best explanation for it, but so whenever you're confused, my advice is to interpret that is forget about interpretation. Just use that as it is. Okay. I'll also need to address what if F changes. So far we are applying constant force. Okay. So yeah, let me split that in a separate video.